Hello. In today's session, we will discuss cooling power. Superconductor magnets have various thermal sources. We need to cool these sources to manage them, and in today's session, we will discuss this cooling process. You can refer to chapters 4.3.1 to 4.3.7 for various thermal sources. Basic concepts regarding cooling include entropy, TS diagram, and thermodynamic cycle. Then, we will move on to discussing cryocoolers. Firstly, let's talk about entropy. Entropy is a well-known scientific concept recognized as a measurable physical property. It is associated with disorder, randomness, and uncertainty. Entropy per unit mass, denoted as S, is the intrinsic property of a substance with a fixed value in a fixed state. Therefore, the change in entropy, delta S, between two specific states remains the same regardless of whether the path between states is reversible or irreversible. Next, let's discuss the TS diagram. The TS diagram represents the change in entropy with respect to temperature during a thermodynamic process or cycle of a substance. In the TS diagram, there are four states depending on the temperature. 1. Liquid. 2. Liquid plus vapor. 3. Vapor. 4. Solid. Additionally, the TS diagram is highly dependent on pressure. Below is a graph illustrating the TS diagram of water. For example, if the pressure is 1 megapascal, water will follow the line indicated by the laser pointer in the table below, transitioning from a liquid state to a mixed liquid and gas state, and finally to a gas state. We've discussed the TS diagram earlier. Now, we can define various processes, cycles, or work on the TS diagram. A combination of multiple processes can be defined as one cycle. The area enclosed by a cycle on the TS diagram or PV diagram represents the network of the cycle. Cryocoolers operate based on the principles of thermodynamics mentioned above. The simple model of a cryocooler is illustrated in the bottom right diagram. When we perform work, denoted as WCA, on the cryocooler, it extracts heat, represented by Q, from the environment at the TOP temperature. Subsequently, the cryocooler releases heat equivalent to Q plus WCA equals QWM to another environment. This principle forms the basic operation of cryocoolers, which can be utilized in superconductor magnets to extract heat from the magnets. Next, let's discuss the performance of cryocoolers. The graph below illustrates the ratio WCP over Q required to maintain the temperature of the magnet as TOP. As mentioned earlier, the most ideal cycle in thermodynamics is the Carnot cycle. The portion marked in blue on the graph represents the performance of a cryocooler using the Carnot cycle. However, in reality, more energy is required than this ideal scenario. For example, according to the table below, to extract 10 Watt of heat at a temperature of 10 Kelvin, using this cryocooler, 10 kilowatt of WCP is needed. There are two main features highlighted in this table. As the power of the cryocooler increases, WCP over Q decreases. As TOP increases, WCP over Q decreases. Using this table, one can determine the operating temperature and cooling cost when cooling superconductor magnets. Next, let's look at an example of an actual cryocooler. Cryocoolers are typically divided into two stages. The performance graph of the RDK 408D2 cryocooler is as follows. Assuming that 40 watt of heat is removed at the first stage and 15 watt of heat is generated at the second stage, we can infer from the graph that the first stage operates at approximately 42 Kelvin, and the second stage operates at approximately 20 Kelvin. In summary, entropy is a scientific concept and a measurable physical property that's often linked with disorder, randomness, or uncertainty. The TS diagram is a thermodynamic chart that shows how temperature, T, and specific entropy, S, change during a thermodynamic process or cycle. The Carnot cycle is an ideal, reversible, closed thermodynamic cycle. Superconducting magnets need cooling because of various heat sources. To pick the right operating temperature, you have to consider the cooling power of a cryocooler and the heat sources. The cooling efficiency of a cryocooler gets better as the required cooling power goes up. With that, I'll conclude the presentation on cooling power. Thank you for your attention.